TPU, which is used in production applications, including search, maps, photos, translate. TPUs also power AlphaGo's historic 4-1 victory over Go champion Lisa Doe. Before joining Google, Dr. Young worked at DE Shell Research, building special-purpose supercomputers for molecular dynamics, and at Bell Labs. He received his AB, MS, and PhD degrees, all in computer science, from Harvard University. So let's welcome Dr. Young.
Thanks for the introduction, Lee John, and also Daniel, thanks very much for the call. Anyway, in your talk earlier, I hope I live up to your expectations. So, we're here to talk about the interaction of AI and computer architecture, and this is my home conference, so it's great to be back at ISCA and thinking about things as a computer architecture person after having spent journeys in different other scientific disciplines, one of which is computational chemistry. I'll talk a little bit about molecular dynamics as part of this talk. And most recently, I've been thinking about AI, which for a very long time I don't think really worked. And now, suddenly, in the last 5 years, has taken off in this incredible way. And so there's this new journey that's on about what are the limits of this thing we're calling AI that is really just the deep learning subset of AI. So why are we all here at, we should figure out how to pronounce this. Is it ADAR or AI, AIDA RC or something like that? ADAR, okay. To ask the question about, can artificial intelligence help computer architecture? And I think this schematic is one way of showing the question. I've drawn the TensorFlow logo here because I come from Google, and TensorFlow, of course, is the framework you should use. But aside from that little bit of advertising, I think of TensorFlow as being representative of an application framework that lets you do deep learning in some effective way. There's been a remarkable sequence of advances in the last few years, starting with just a couple of things that happened in speech and vision, which gave us at Google the hint that, yeah, maybe this is something real we should do something about before we're buried in a flood of neural network inference workloads. But then the breakout has been huge. We are doing things in translation, in search ranking, in playing the game of Go. We're looking into things in robotics and self-driving cars, or analyzing the road and what they see from the panoply of sensors using neural network techniques. There are really encouraging initial results in medical diagnosis, which I'm hoping will transform that world into something which drives the healthcare business. And there have even been exoplanets discovered using neural network techniques. And so it seems like every day I turn around and I read a new article about, or read a new press release or news summary of a breakthrough in this field. So artificial intelligence has been driving surprisingly general breakthroughs in a variety of fields. We at Google have been building our own machines. The picture on the left is a board for a third-generation tensor processing unit, which happens to be liquid cooled. Ooh. These TPUs are fueling the neural network revolution at Google. And of course, the big question that I'd like to engage with, and we're here to talk about in this workshop, is can we close the loop? Can we fire off a virtuous cycle where we figure out how to do a little bit better design, and that makes our TPUs, or whatever PUs, just a little bit better, and that allows us to do better neural network processing in some sort of, I said virtuous cycle, but takeoff effect, some sort of self-reinforcement effect that might carry us through the next few decades of computer architectural development. So I should probably give the caveat, I don't know how to do the AI for computer architecture. So if you thought you were going to have a talk about, here's how we've already used it to build TPUs, that's not this talk. I think a bunch of the perspective on this is, what are the design problems we are solving for building these special purpose computers? What do they look like? How do those problems interact with the things we think we can solve with AI? How do we put those set of puzzle pieces together? Where can we start making progress? So I structured the talk as 3 journeys through the topic of co-design. Raise your hand if your advisors mentioned the concept of co-design, or you've had it beat into you since you began graduate school. Okay, a good showing. And we see co-design throughout the literature in our field, the hardware-software interface, the instruction set architecture design. I'm going to talk about co-design in 2 contexts for machines that I've worked on before. The first in molecular dynamics, or a branch of computational chemistry. We built Anton machines for 10 years of my career, 2003 to 2013. And I'm going to attempt to coin a term here and talk about radical co-design, which goes beyond just the hardware and software pieces to encompass algorithms and applications as well. Then I'll talk about our current state of the art in TPUs, a journey I think I've been on for about 5 years, and at this rate it looks like it's going to continue for decades. Where the constraints are slightly different, the science is slightly different, the target is a moving target, much more so than it was in the computational chemistry space. And for the third leg of the talk, I'll come back to the journey we're just starting about ADARC, about systems driven by ML. Inside of Google, my tiny piece of this we're calling Learn to Accelerate. If you talk to the neural network researchers, they think architecture means something entirely different. They think architecture is model architecture. So if you say learn to architect, that's actually a name collision. And so Learn to Accelerate is the thing we focused on. So let me talk about Anton machines first. The first journey, radical co-design for molecular dynamics. So raise your hand again if you've heard of Anton machines at all. Okay, also a decent matter, but I should give you the background about it. In ISCA, more than a decade ago, we published a paper about our first Anton machines, which were built at a place called DE Shell Research in New York. It was a special purpose computer for molecular dynamics simulation. And while today special purpose computers are not uncommon as a direction where we think we need to go because Moore's law is running out on us and we need to find high volume, high benefit applications and customize to them because we can't seem to push our CPUs that much further. In that time frame, in 2007, or worse yet, in 2003 when we started the project, special purpose computers were crazy. You wouldn't do that because Intel had won, and Moore's law was going to make sure that Intel machines got better by a factor of 2 every year. And so that was, to have built a special purpose machine in that time frame was a little antithetical. And to compensate for the beneficial effects of Moore's law, a factor of 2 in transistors and performance every 2 years, a factor of 10 every 5 years, we said we'd better design a 1000x machine because it's going to take us 5 years to build this thing. And so if we design a 1000x machine, then maybe during those 5 years we'll lose our 10x, but we'll still have 100x left over afterwards. So one of the explicit targets was, can we speed up existing National Labs class supercomputer machines by a factor of 1,000? And the answer to that question turned out to be yes in 2008. So 1000x is a transformative difference. It's not the sort of thing that you do by tweaking a few execution units or changing your ISA just a little bit. It requires reconsideration of the model machine. If you read the first Anton paper, there's a very carefully reasoned set of discussions about why we thought there was an opportunity, how we would build that machine. I de-emphasized the hardware link on this page, not boldface like the other things, because you can read all the specs. It's kind of cool that it's a 512-way supercomputer that has a 3D torus interconnect. It had awesome register-to-register latency from a core on one chip to a core on another chip. It had, for its time, relatively impressive bandwidth and multicast things. But I'm getting distracted about the hardware stuff because we're hardware people. I think that a bunch of the key contribution in the Anton project was not the specifics of these super cool things that we built, because those stats, while better than many supercomputers at the time, are not the fundamental thing. I think the fundamental thing is the algorithmic and application co-design, that we looked at numerics and changed them, that we looked at the fundamental algorithms that you use to evaluate electrostatic forces in these physics simulations that we were doing and changed them. And then we changed the hardware in turn, or in concert with the algorithmic changes, to come up with an overall solution that was better. So this slide sketches some of these. The numerics in Anton machines are largely 32-bit fixed point, although there's a bunch of shaving inside of the special purpose functional units to get that much narrower, to allow much higher density of those units. And there are algorithms with obscure names: NT method, Gaussian split, U-wall, constraint integration, oh, and the FFT. You've probably heard of the fast Fourier transform, but I have a little bit more about that in the next slide. So I'll come back to numerics in a little bit. The neutral territory method is an algorithmic change that transforms the communication pattern of your parallel machine. And for the particular case of atoms exerting forces on each other because they're electrostatically charged, it changes what looks like an n cubed amount of communication into an n to the 1.5 amount of communication. So that's intuitively shown in this slide, that if you think that you've got atoms in the dark box that want to interact with some radius around them, you probably have to import this plate around the place that you're working. But it turns out that you can actually do much less communication involving only these two spars sticking out of the original place. And every interaction pair of atoms will actually still be covered somewhere on the machine. So it's a restatement of how you parallelize that turned out to change our bandwidth requirements. And by virtue of changing our bandwidth requirements, it changed our machine from being totally bandwidth bound on the best links you could possibly apply to being sometimes bandwidth bound and sometimes latency bound. In other words, somewhat balanced for the way we were building our supercomputer. And you know, these were not cheap links. It wasn't like throw more money at it and you'll get more bandwidth and be able to solve the n cubed problem. It was do this to get the machine to work at all. A similar actually, a different algorithmic change that allowed us to save hardware is called Gaussian split AWOL. That's got a lot of math behind it that I probably shouldn't go into, but the main thing is that the standard AWOL sum from particle mesh used splines. And splines tend to have these quadratic or quartic-like equations to them that are bound to the grid that you've divided space into. We restated the AWOL sum with help from our chemistry team to do something which is spherically symmetric. So just a function of the distance between two particles. By doing that restatement, we took 3 different special purpose subsystems in the original design of the machine and fused them into one, which saved us something like 50% area, 15% area, a bunch of designers and design verification resources, a bunch of coding, and as it turned out, didn't cost us any time in the machine. Another example is constraint integration. It turns out that it helps you in these simulations to make water molecules look like rigid triangles. That's a calculation that turned out to be most efficient on general purpose cores. So we put general purpose cores into our machine. And maybe I'll just mention briefly, the fast Fourier transforms on Anton machines are not the ones you do benchmarking on because they're too small. There's only 32K points spread across 512 nodes, which is basically 64 points per node for the Fourier transform, which means you're almost entirely tiny packet dominated on this communication network for the machine. We built a solution on top of our ridiculous network and those programmable cores that does I guess that should have been 32K points on 512 nodes in 4 microseconds, which fit into our time step schedule. So coming back to the radical co-design theme, what does it mean to do radical co-design? It's difficult to do radical co-design within the space of one ISCA paper. I think to come back to what Lee John said and why giving some of the more industrial perspective, you need to be building a whole system to be able to consider things top to bottom, to adjust the hardware and the software, the algorithm and the application all at the same time. It also helps a bunch to have the luxury of time. One of the nice things about the molecular dynamics project was that it didn't have a huge amount of competition going on. It wasn't a super hot market, and so we could take the 5 years to design the machine. We could take the time to understand the math that the chemists had handed us and look at and push back. Do you really need to calculate this thing in that term, which is n squared? Can we find a way to restate it as m log n? If you have the time to do that, you can make an attack on Amdahl's law limitations iteratively. So if you're doing good engineering, then you have a profile of your workload, possibly from a CPU trace. And there's a breakdown of tasks using usual statistical distribution. So some tasks take 60% of the time, and some tasks takes 30%, and then there's a 10% task and a 6% task, and so forth. If you're in the software business, you probably spend a bunch of time heroically optimizing the 60% of the task. And by doing that heroic optimization, you speed it up by a factor of 6, and now it's a 10% task, which means that you could probably work a little bit more on the second task that takes up 30% of the time. But you really should stop at some point because Amdahl's law sticks, right? Your optimized software is only so fast, and you're left, like, it's not even worth looking at the 1% tasks. I'll contrast that with what we can do in architecture, at least in special purpose machines for architecture, where you can throw hardware at a problem until its time effectively becomes 0. So take the 60% task and make it 0. Now your 30% task dominates your profile. Attack the 30% task, possibly with a different accelerator, make it 0. Keep on doing this. This is the way you get to a 1000x machine. I found myself designing hardware units for 0.1% tasks in the original supercomputer molecular dynamics profile, stuff that nobody else would be optimizing. We were saying, we build a hardware unit for that, which in some ways is crazy, and in other ways is exactly what you need to get to the 1000x. So that's one version of radical from a system and profile-driven perspective. And I've said it a number of times, not just hardware-software trade-offs, but algorithm application. And so the numerics bits about can we replace float 32, int 32, and then shave the int 32s down to int 5s and int 6s in some parts of our design, required that freedom to say to our chemists, hey, if I debase the currency, if I throw out this part of the ALU, is it still doing physics as far as you're concerned? If I change that communication algorithm, am I still getting exactly the same mathematical terms, or am I getting close enough mathematical terms to still do the job? An entertaining aspect of building the solutions to the 0.1% tasks is we eventually had a design that had 7 different functional units on it, which we couldn't possibly fit into the chip area. And then reality comes in. How do you build an actual system to solve this problem? You throw stuff overboard or deduplicate. It turned out that those 7 units didn't need to actually be 7 units, and we eventually refined them down to 2, the 2 blue boxes in this chip diagram, one of which you might call a very special purpose system, kind of like the matrix unit in the TPU. It actually did particle-particle interactions. and one which I'm pointing to the wrong one. This is the specialized system. And one which was called the flexible subsystem, which was a chip multiprocessor with 13 cores on it, which also, by the standards of the day, was incredibly specialized to the chemistry application, but specialized in a way that paid off for each of the particular calculations. Each unit that we put down into this 13-way multiprocessor was targeting a particular part of the time step, again, with that relentless focus on latency to deliver a solution for our chemists. So maybe another piece of this is solve the chemist's problem, right? So we within architecture have an appetite for borrowing techniques from nearby fields and using them. I think a bunch of our profiling stuff and some of the control theory stuff and some things that come from networking influence how we design our hardware units. But this is not solving our problems for us. This is solving the other guy's problem. It kind of requires putting down your own pet approaches and saying, what do I actually need to get out here? And one other observation about the molecular dynamics space was that there were no revolutionary algorithmic changes in molecular dynamics, possibly over the last 15 years. That in some ways made it easier because it wasn't a moving target, which brings me to TPUs. Okay, so that was journey one, molecular dynamics, computational chemistry, radical curve. Let me talk about a journey we're still in the middle of, which is doing tensor processing units for deep learning at Google. Last year at ISCA, we published a paper on our first generation tensor processing unit, which the story for that is averting the neural network inference success disaster. And so, raise your hand if you've heard the term success disaster. Okay, I should explain that. So the success disaster is, I've found this thing with which I can change the world. All I need to do is deploy to Google scale, and I can change the world. And so the problem is, how do you build a thing that you can deploy at Google scale? So the success disaster in 2013 was that speech and image processing were working. Right? So what happens if speech takes off and everybody starts talking to their phone for 3 minutes a day? What happens if image processing takes off and everybody wants to analyze a minute of video per day? We did the back of the envelope calculation, and it turned out that it was the answer to process all of that work was multiply the size of Google data centers by a large number, 2 or 3, possibly even more, given that those are relatively conservative estimates. If you're Google, do you want to go and double or triple your data center spend, which shows up in our bottom line? The answer is not if you can avoid it, not if you can come up with alternatives. And so that success disaster is, I can change the world. It's incredibly valuable to do this, but I'm not positioned to be able to do it without just the only scaling dimension of spending more money. Can we give ourselves other potential investments that give us options to deploy and avert that success disaster? So because of that impending success disaster, we had an incredibly tight schedule for the first generation TPU. 15 months from project kickoff to it's running in the data center with customer code. The hardware, as we described in the paper, is relatively simple. The big thing is there's a gigantic matrix multiplication unit using systolic array matrix multiplication. And if you look at the block diagrams of the machine, which I didn't copy here, there's just enough everything else. Support for activation functions, pooling, normalization, weight memory, to be able to evaluate a neural network inference. We were careful about system design issues. This thing is built as a coprocessor. It hangs off of the PCI Express bus, but it was also built so that it could contain enough state so you don't spend all your time hopping back and forth. Something we learned from the GPUs. I think early GPU deployments, you could take your 60% kernel and put it on the GPU, and then you'd still spend all your time going back and forth between your 60% on the GPU and your 40% back on the CPU. That didn't lead to a speed up until people figured out how to move the 40% onto the GPU. So we looked at the 40% for neural network inference and said, how do we capture enough of that? Maybe not actually all of it, there's still a bunch of stuff that runs on the phone, but enough of that so that you can get ahead in running on GPUs. The other main thing besides this gigantic systolic array matrix multiplier was numerics. We went with 8-bit fixed point. That had been shown to work at least for the speech subset of the market. Actually, the speech results were mixed. They said, you need 12-bit some of the time, you need 8-bit some of the time. We looked at that and refined the results as part of the design of this machine. Said, we are pretty sure we can get by with 8-bit, but we're gonna have a chicken bit. We're gonna be able to bail out and run in 16-bit mode 2 or 4 times slower, depending on where the 16-bit parts come from, in case something comes up that fundamentally requires it. If you've read the paper, the key limitation on the TPU is actually not this gigantic compute unit or the accuracy of the numerics, but rather that we went with standard DRAMs in the design. So I think underneath the heatsink, there are DRAM chips soldered on the board. They have relatively miserable bandwidth compared to the performance of the matrix unit. You actually need to, for any weight that you read out of that DRAM and use on the machine, you need to reuse it about 1,300 times. In other words, if you're doing neural network stuff, you need to find a batch size of 1300 or a matrix side length of 1300 in order to actually hit peak on this machine. And so it's not a balanced machine. It has this great 92 teraop peak operation for, calculation rate, which we only hit in a couple of interesting applications. Another thing about TPU v1 though is that the inference problem is much, much easier. Inference scales out. This thing is big enough to run any of the models that we have. And so if you want to serve at Google scale, you can drop one of these into some fraction of your fleet, and that builds you a serving solution. You don't have gigantic system design questions. On the other hand, the second generation TPU, which we announced a year ago, is much more ambitious. So I mentioned neural network inference. I think one of the other speakers drew a distinction between neural network inference and training. Are you guys all familiar with inference versus training? Construct the model part versus the evaluate the model part? People are not, so I'll skip a little bit over that. The problem with training is that my brain colleagues are ambitious neural network researchers and nothing is ever good enough for them. So if you buy a cluster of GPUs and you fill them up and they say, can we go faster, can you buy us better networks? There's always going to be somebody who says, if only I had a larger set of weights or a larger training set, I could do so much better. And in fact, that's been part of the history of the the deep learning field, that the combination of giant data and ridiculous processing has unlocked things in ways that we had not seen before. So this seems like a dimension to invest in, especially if you're Google and you're already familiar with scale, willing to double down on scale. This is a reasonable thing to do. So TPV2, because it's doing training, which is 3 times the work and much more complicated than inference, it has to be more general. It has to be more flexible, more programmable. There are things that are going to change in your training loop. That requires us to back off from some of our specialization and think hard about our trade-offs among compute, memory, and network. We're still doing systolic arrays for matrix multiplication operations. We actually buffed up the everything else. So if you look at the block diagrams for TPV2, it has a vector machine next to it, and a scalar machine next to that. And you can imagine that there's division of labor among the scalar vector and matrix units, and careful choreography of data over the network to make that particular machine sing. We're embracing multi-chip parallelism. We have an aggressive interconnect. You can see the connectors here on the edges of each of our boards, and you can see the wires in the rack scale deployment of what we call a pod, which is actually a supercomputer class machine. One other note, we switched from DRAM to high bandwidth memory, which is a core GPU technology. That gave us 30 times more bandwidth than the previous generation machine. So in the reviews for the TPU v1 paper, we did a little bit of talking about, yeah, if we improve the bandwidth of memory, it would get better. I think at this point we can say, yes, we improved the bandwidth of the memory by a factor of 30. So the new machine at least addresses that particular identified bottleneck, as well as a bunch of other ones that we haven't talked much about. And the summary of TPV2 is, yeah, we're spending on all 3 of the computer architecture dimensions. We're putting ALUs in, we're putting aggressive memory in the form of HBM. We have this interconnect that ties these machines together for the gigantic scaled-out training case. This really is a supercomputer class machine for machine learning. Only a month ago, we announced that we've already built a 3rd generation TPU. We've said precious little about this publicly, aside from the fact that it's liquid cooled. That's what these hoses are. So these are cooling blocks. One of the ironies of showing these off in public is that people think that TPV2, because it has giant air heat sinks, is the more recent thing, because the heat sinks are bigger than the cooling blocks on this. So sometimes physical size doesn't actually correspond to what's the most recent, more aggressive thing. More heat corresponds to more operations being done. I think that's about the limit of what I can say. The other thing is that we've increased the scale, and so this is 8 racks instead of 4, so there's another doubling there in capacity for this insatiable demand for cycles from our neural network colleagues. We expect to iterate rapidly. The tick has been a little bit over a year for delivering each new generation of these sorts of things. And I should perhaps emphasize that TPUs are real computers now. They incorporate connections back to CPUs in the general purpose world in our cluster networks, but they also have to sequence, they have to decide, they have to predict, they have to manage resource trade-offs in ways that standard computers do. So unlike the molecular dynamics case, where the algorithms have largely stayed the same for maybe the last 15 years, and that's not giving full service to my chemistry colleagues, but I think we could all agree that the deep learning revolution is a moving target. And an illustration of this is that there's a Moore's law for papers in the AI field. This graph is actually time on the horizontal axis and the number of submissions to archive relating to machine learning in the vertical axis. So the rough curve is just things that fell into those buckets, and the fitted curve is a standard Moore's law curve. So the number of just ideas being published in this machine learning space is going up exponentially, which is kind of crazy. Presumably also doesn't scale to some unknown limit because there's only so many humans on the planet, but I think we've exhausted that resource so far. I think that our TPUs are still relying primarily on those two things that were in the very first TPU: systolic array matrix multiplication and reduced precision arithmetic. Maybe another beautiful structural thing about TPU design is that the problem area, deep learning, admits to a small number of primitives. Really, there's matrix multiplication, and there's the activation functions and some pooling and striding kinds of things that help you do column nets. And that's really the set of primitives you need to support. You could haggle about what other things need to go into the machine, but it really is a very focused set of things that if you do them great, you can build an effective system in this space. We spend a bunch of time attempting to generalize our machines through buying domain-specific insurance policies. So TPU 2 and 3 are more general-purpose machines, but the insurance policies mean that we're aware of things that are happening in the researcher field, and we add architectural features that attempt to address those. So one example of that is we added last-minute support to LSTMs to TPU v1. We actually generalized the number of activation functions that we performed, and we added support for element-wise operations in a terribly last-minute hacked-in part of the architecture. But what that meant was that we could run LSTMs, and that enabled a bunch of breakthroughs in both speech and translate. Inception, which is also known externally as GoogleNet, changed the way that people built neural networks. In 2013, when we started the TPU v1 project, everybody built a stack of layers, right? It was a stack of convolutional layers followed by a couple of fully connected layers, or it was a stack of fully connected layers in multi-layer perceptron shape. The Inception paper said, let's make it a graph. And so if you had designed the machine to assume that everything was just a stack of layers, you might have made architectural simplifications that killed you. It made it irrelevant to doing stuff like Google Map. As it turned out, we had enough of an instruction set and enough of the notion of reuse and abstraction and pointers in the architecture of the machine that we were able to map GoogleNet and also the LSTMs to the first generation TPU. So I think there's a balance here that the neural network researchers would call being careful about generalization versus overfit. You don't want to say, the set of problems I'm working on right now is a set of problems that I'll be doing 3 years from now. Instead, what you want to do is fuzz things up a little bit and think about what are the trend lines, where are the research ideas that might take off that you'd want to invest in, and possibly put an insurance policy into, something which might not cost you that much hardware-wise up front, but which, if it turns out to be real, you could do software payments for it to make it real later on. Let me skip the alpha a little bit. How am I doing? About 15 more minutes? Okay. Okay. So I don't actually think that our TPUs or any of the neural network accelerators have engaged in what I would call radical co-design. Part of that is, can we break the application, or can we change the application as given? Are we taking the source code that's written as things are today and just saying, yeah, we'll just implement that? Today, we're just doing stochastic gradient descent, as our researchers say. We're just doing optimization algorithms like Adam and Agrad, like they say. But we already know we can break things, right? We bet on int 8, and in NVIDIA GPUs there's float 16 support, and in TPU 2 and 3 there's bfloat 16 support. So reduced precision works for us. We think we're done, right? Each of these, int 8 versus float 32, is a factor of 4 memory storage win, and maybe a factor of 16 compute area and power win. So is that the lower bound? We actually don't know. We're not doing that many studies to figure out where that lower bound is. My personal bet is the lower bound is below 1 bit, which also might seem crazy to you, but why should the lower bound be below 1 bit? Because we think sparsity is going to work in some way, right? That you don't actually need all of the bits, every neuron in your fully connected layer to be represented by a single bit. It's probably the case that some of those drop out. Some of those get thrown away or pruned away as part of the learning process. We're not spending the time to understand that. Or we're not spending enough time to understand that because we're so busy exploiting the current practical application. Sure, throw a power-guzzling GPU or TPU at these problems because they're practically valuable now. But how much better could we do if we were actually efficient about it? Similarly, for algorithmic co-design, we are figuring out parallelization. If you looked at the predecessor of TensorFlow, which was called distbelief, there's a beautiful paper about asynchronous stochastic gradient descent. And ASGD is a wonderful algorithm for dealing with the huge variation in performance across CPU cores in Google Data Center. Because Google Data Center has a pile of machines, each of which is running many different random workloads. The performance deltas between one machine, one core and the core next to it can be factors of 1,000. In that environment, if you want to do parallel training, you have to account for those factor of 1,000 speed differences. And asynchronous SGD means that things don't work in lockstep. You break the central lock in your parallel computation and allow things to send updates when they can. That was a great adaptation to Google data centers, but it turns out that if you're building a supercomputer, you don't have to worry about those competing loads or that factor of 1,000. Or if you have a factor of 1,000 speed difference between one TPU core and another TPU core, your slower one's broken. You should throw it out and go put a working one in. There's a bunch of interesting research going on about batch size. I think GPUs and TPUs run at a relatively high batch size because that makes their matrix multiplications efficient. There are some cool startups emerging that are aiming at the batch equals 1 point. I'm not sure whether they're going to prove things will work, but I'm very much looking forward to playing with the things that they build. There's also this aspect of the field where everybody thinks they have a version of sparsity that's going to work, and everybody agrees that sparsity is important, but if you ask N researchers what they mean by sparsity, you will get N+1 answers. So just to mention a few, ReLU induces sparsity. Pruning of various kinds, of which dropout is one, induces sparsity. Traditional numerical compressed sparse row representations, that's compressed sparse foo representations you can look up, are another form of sparsity. There's block encoding that Scott Gray cares about. Embeddings are actually a way of dealing with sparsity. And in fact, attention models, which are what power our translate systems, also involve a form of sparsity, or at least you could implement attention sparsely if we built the architectural structure to do it. There's a spectrum from completely hardened attention, which is just a load, to soft attention, which is what we build today, where we load an entire matrix and then do a weighted sum over the rows of the matrix as part of evaluating attention. So I think we really don't understand what we're doing in these machine learning calculations. We don't know where the fundamental limits are, where the equivalent of information theory's channel complexity or fundamental entropy limits are in these neural network training calculations, or even in the inference calculations. And we see great research about this on the inference side, where you can compress the networks to nothing, or compress them to binary or ternary values, I guess. But the training side, I don't think we've seen as much of. There are what I would call tantalizing hints. If you've seen distillation, it's train a big model to a certain level of accuracy, and then use the big model that you've already trained to train a much smaller model to a similar level of accuracy. By using distillation, you can get the small model to a higher level of accuracy than you could by directly training it. What does that mean? I mean, some of that means that models are compressible. I think some of it means that the extra parameters in the big model give you freedom that makes it easier to train. So maybe distillation, like train then distill to get from the large to the small model, is the fundamental thing we're going to have to do. But the research into why does that work hasn't been plumbed, hasn't told us anything that's actionable as far as computer architectural hardware. Probably means you build different training and inference machines. And maybe it means you build different training and inference machines. Or maybe you need to build a training machine that's flexible enough to have more degrees of freedom for training and then to prune down and still operate efficiently if you then go to the smaller model view of things. There's a great paper in the last month from Uber about intrinsic dimension, which basically says the number of weights you need in your neural net model seems to be induced by the problem you're working on, regardless of what structure your model has. And that's worth looking into. And there's a completely crazy result called feedback alignment, which says you don't actually need to do backprop as we traditionally do it. Are you guys familiar with backprop? Am I talking too much like a neural network person? Like some people are raising thumbs, not too many. So backprop is how the machines learn. You do a forward propagation, you say, here's a picture, and the network propagates through and says, I think it's a cat. And then you tell it, no, that wasn't a cat, it was a dog. And the backprop signal, you run backwards through the network by taking derivatives, and you adjust your weights ever so slightly. So when you're doing that backwards running through the network, you typically take your weight matrices and you transpose them, because you're taking an error signal and running it backwards through the network. The completely crazy thing about feedback alignment is you don't have to use the transposed weight matrices to do the feedback. You can just use random matrices to do the feedback, and the thing still trains. That means that there's something really weird going on with backprop. That we don't actually need numerical backprop to still do training. And I guess the other biological hint is that we're pretty sure that brains don't do backprop. So we may be doing machine learning that's inspired by actual brains, but we're not really doing anything like what our brains do. Open research on the biology side. Anyway, my point about these kinds of things, which are hard for architects to think about, but part and parcel of building these special purpose accelerators, is that we need to be doing more methods research. we need to be doing more of this investigation of the algorithms and the numerics, and doing so in a way that embraces the whole system to solve the problem. We are just about at the end of Moore's Law. We're going to run CMOS and digital arithmetic as far as we possibly can, but at some point we're going to hit some transistor wall. And at that point, we can't just say float 32 is the answer to all these things. We're going to have to get a lot smarter than that. Okay, so journey 3, can ML help computer architecture? The reason you guys all came for this talk. So I think that there's a span of design problems. Li Zhang was saying, we're here at this conference so we can automate ourselves out of jobs. I think that there's a huge gap between what we do today with ML and what we need to solve in architecture. And we're just beginning to get the two fields together, and so there's only a small set of problems that actually work. So I'm not terribly worried about our jobs. I kind of feel like the how do you learn the algorithm, how do you think about the math, is still a thing that people need to do. I think there are some things which look like design space exploration or the tedious work that we're terrible at, that machines are great at. Maybe one intuitive way of saying this is, I personally, as an experienced designer, think that I can optimize 2 or 3 things at once. I really, I think about bandwidth and latency at the same time, and then I've got a really good system because I'm optimizing for both. And bandwidth and latency are in many ways very different qualitative things that you have to think systematically about, so maybe that's where I add value. The machines are great at optimizing 1,000 or 10,000 things at the same time, at pulling out diverse signals and integrating them, but they have to do it in a way that is supported by these digital frameworks. You have to build the search space or the design space for them to make progress, and that maybe is what our job switches to. It switches from find the question, propose a solution, evaluate the 3 possible answers, and pick the third, one of the 3, to find the question, propose a search space of thousands or 1e, 60 possibilities, let the machine learning algorithm search the space and come up with solutions, which is, I think, a bunch of what Daniel was talking about in his keynote today. All right, so rather than going into huge amounts of detail about this, oh, I'm sorry. I have a little bit more of my story about this. So as I mentioned before, the machine learning breakthroughs keep on coming, and I listed a few that are my favorites here. Back in college, I read a book called The Structure of Scientific Revolutions, which is huge in the philosophy of science and history of science field. And Kuhn's book from the 60s talks about how science moves in 2 ways. What he called normal science is sort of the thing you go to grad school for. It's kind of go to grad school, learn how to use your test tubes and the pipettes and machines and so forth, and do, I don't know, gel plot experiments or whatnot. Contribute your papers. If you're at ISCA, make sure you include enough bar charts in your paper. And every once in a while, like once a century, a field undergoes a radical thing called a paradigm shift, where somebody says, huh, that's funny, that doesn't make sense, and pulls on a thread and leads to a new model where suddenly all of the old normal science mechanisms and tools don't quite work. I think that machine learning looks a lot like this, like the midst of a paradigm shift, that speech and vision processing had particular methods for doing their tasks before, and they worked up to a certain degree of accuracy, and then the first machine learning models start to work and they blow those levels of accuracy out of the water. And we keep on seeing these breakthroughs happen. So I think the interesting thing is there's this new tool. It's not explainable. It uses a lot of flops. It explores gigantic search spaces. So it's not what we're used to doing with our simulations necessarily, but I think it's worth a while to go and dig into it. So as a personal aside, and the way I think about this, I feel like the 2 co-design examples I gave you for Anton machines and TPUs only work because I have a bunch of colleagues who are incredibly curious, who are not just computer architects, but were willing to say, yeah, I'd like to learn about chemistry. Or, yeah, I'd like to learn about backpropagation and that particular scary part of continuous mathematics that I ran screaming away from when I was doing my undergraduate work. So that curiosity carried us far enough to build those systems. And this application-focused co-design requires learning lots about the applications. It really is worth your while to get to know the chemists or the neural network researchers. It's better still if you can teach them our tools. Like, hey guys, there's this thing called Amdahl's Law. It's totally worth thinking about if you want me to build you a machine that's 1,000 times faster. And it's also worth understanding their constraints. Like, how do temperature and pressure relate in this? And why do we want to control both of them? Or what do you mean when you say generalization? What do you mean when you say learning rate? What does that do? Because those concepts translate into specific things we care about. Learning rate, for example, is something you want to represent numerically. And should you represent it with a floating point value, or should you represent it implicitly because it's hidden somewhere in the way that you push things through the hardware of your machine? And another piece of advice here is embed the random conversations in the hallway with your chemistry or neural net colleagues lead to great insights. The next step, learning to architect, I think is even bigger, scarier, and harder because instead of drinking enough of the Kool-Aid to have an interesting conversation with my colleagues, I've got to be a neural network researcher. It helps to have great collaborators. I think Google Brain Team is a pretty good place for finding people who are at the tip of the spear as far as neural networks go. The nice thing that reassures me is that I still am working in my old field. I'm still building machines, right? I'm still building systems. It's just I'm hoping to use this new tool in it. So, as a view of what's working well in machine learning, I think it's important to point out that really most of the successes today are in what's called supervised learning, where you have a huge set of labeled examples that say this picture's of a fish and that picture's of a cat, and labeling is hard, and huge data sets are hard. And a bunch of these deep learning approaches use stochastic gradient descent, which requires differentiability. These supervised learning techniques, I think the most cool thing about this as far as intelligence goes is that Translate seems to be dealing with syntax. So if you look at what makes humans unique, everything else the animal kingdom does except syntax, right? We have culture, some animals have culture. We have tools, some animals have tools, some animals have opposable thumbs, some animals teach their young to do things, and so forth. We have syntax where complicated linguistic structures mean different things depending on the order of words, and no animals do that. Translate is starting to do that. Now, we can't explain why. It doesn't explain what it's doing when it's translating English to French, but I think there's evidence of sophistication there. The other thing that I'm going to talk a bit more about is reinforcement learning and evolutionary strategies, which relates to the state space exploration thing. If you have any reward function, you can actually use RL to do optimization in it. It does a sort of combinatorial optimization or space exploration. And we've seen it pay off hugely in the AlphaGo case. AlphaGo is a little scary because it's definitely doing strategy. Right? It's got both short-term things about which move to play now, and it's got something going on about long-term that, again, we don't know how to explain how it's doing that strategy. But this gives me hope for solving complex hierarchical problems or complex problems at the scale of our devices. Go is combinatorially vast, right? It's 361 factorial possible games, or maybe not interesting games, but at least possible games. That's crazy. But in some ways, it's small compared to the design decisions replacing 2 billion transistors. So we can take an illustration from their example, and maybe we can steal some of their strategy, but I don't think what was reasonable for Go is actually going to help us completely design our machine. How do we use these things? All right, so I'm running low on time. Each of these 6 points I have a backup slide for with way more detail, but I thought I'd go through these quickly in the interest of time and leave some time for questions and answers in the talk. So, brief research suggestions. Apply supervised learning and or reinforcement learning online and on device. And I think Daniel said this in his keynote earlier. There's piles of data online and on device, so let's just use it, right? But find ways to do the studies so that you can use the training data about what was the correct path to take, what was the correct instruction to schedule, what was the right block to load into your cache. Use RL and evolutionary algorithms for design space exploration. In some ways, the AlphaCo game playing strategy is a form of design space exploration. It's a little weird because it's adversarial, right? There's I play and you play and so forth, and so I have to anticipate your parts of the cost function. But in other ways, it has interesting tree structure to it, just like our design problems do. And so maybe something about Monte Carlo tree search could inform our design processes. Or maybe something about branching down pruning should inform our design processes. I wonder whether our job shifts from design the thing to specify the space of things, and then let the algorithm find the surprising solutions within that space. In some ways, that's not just ask the question, but also say, well, I can format a set of possible answers to this question. Of course, replace heuristics with machine learning systems. I had a quote about this, which is misquoting Jeff Bezos instead of your margin is my opportunity. I think your heuristic is my opportunity is something that we might take to heart in this community. That what's a heuristic? It's something a human looked at and said, well, I don't know how to solve this exactly. It's uncomputable or NP hard. Let me come up with a rule of thumb that works in most cases. And so what is least recently used except a heuristic? What is earliest deadline first except a heuristic? In fact, systems as a whole is lousy with heuristics, and they have these 3-letter acronyms. Anytime you see one of those, you should probably say, wait a minute, can I do a better job on it by learning, by using data to pick a specific solution? And maybe that's just what profile-guided optimization has been. Maybe our dynamic optimization systems are exactly this. And so we've had machine learning in our machines all along. Okay, rebuild tools to enable and expose more design space exploration. One of the terrible things about the engineering we do now is we engineer to solve once, right? You build the compiler, you get the thing to produce -0 code, it's correct, we're done. right? And the terrible lie of the compiler field is we call it, you take the -0 code and make it -04 code, we call that optimization. But it's kind of making it slightly less bad. It's not actually optimal in any sense of searching the whole space of optimization. And part of that is that the engineering is hard, that we need to make things always be correct for compiler purposes, and we don't engineer our compilers, therefore, to explore the space of possible solutions and choose among that space of possibly correct solutions for ones that are interesting as far as performance or cost or whatnot. So I think that that might be a huge amount of work to do that re-engineering, but it might be the thing that unlocks a bunch of our ability to apply these reinforcement learning and search space kinds of things. We have the metrics, right? You just ask the compiler, how long do you think the schedule took? You can ask the simulator, how much energy did this cost? So that's actually a relatively easy part from our view of using RL. Two last things. So close the timescale gap between microarchitecture and ML. I was thinking of asking Daniel this during his keynote, but most of the structures we build, or we think about building as architects, operate in the cycle range, in the nanosecond range, maybe the 100 cycle range for some cache misses at some levels of the hierarchy. Our current state-of-the-art machine learning prediction things at best run at the millisecond to microsecond range, right? So a bunch of the production networks we deploy at Google are so the millisecond in data center cases and microsecond for some of the cheaper kinds of things that we want to run. That's still a factor of 1,000. So can you close the gap? Can you get things, also, no, I'm sorry, that was just the inference side. The training side is worse, right? It takes hours to train a neural network on a supercomputer class pod. It takes days to weeks for a typical researcher with a GPU under their desk. So that's too long, too slow. Can we build better structures or come up with better algorithms so that those days and weeks become milliseconds or nanoseconds? Sorry, become milliseconds, microseconds, and nanoseconds. Can we bridge from the ML we're already doing in the perceptrons and our branch predictors up to the bigger time scales? Maybe some of that starts with looking for longer-term behaviors. Like maybe we should start with OS scheduling. The Tim Kraska B-tree paper is about millisecond-level disk accesses. And so he's doing neural network predictions which take less than milliseconds to figure out which thing to load next from disk. And because disk accesses are milliseconds long, that's the right cost trade-off. But if we made the predictions cheaper, then we could attack more problems. Okay, and lastly, remove barriers between CPUs and TPUs. And this is wild speculation, but I mentioned that our TPUs are becoming more general, more programmable. You already know that our CPUs have machine learning things in them, typically running at the cycle level. Suppose that this Kuhnian revolution, the deep learning thing, really is a paradigm shift in how we do all of our computer science and systems engineering. If that's the case, do you really think that CPUs and TPUs stay separate forever? Do you really think that they're over a PCI Express bus in a car far away? Or do you think that they're each going to move towards each other, adapt each other's techniques? Maybe it's a Reese's peanut butter cup. You got your TPU and my CPU, and that, wow, it tastes great. But there's probably some sort of architectural fusion that's possible. How do you enable that sort of architectural fusion? Well, first of all, find ways to closely couple general purpose compute into your accelerators, better than PCI Express. I think the mobile people building systems on chips that fit into our phones are likely to get leverage on this before the data center people do. The other aspect of it is, can you put TPU-like functionality into a CPU? So we have branch prediction units, and we have prefetching units, and we have cache-like units. Is there something that looks like a generalized prediction resource that might live in the CPU space? And if so, what does it look like? Like, how do you ask it questions? How do you give it feedback saying, nope, bad predictor? How big is it? How much of your chip area are you willing to spend on it? How does it switch contexts or maintain indexing? I don't know, but that is part and parcel of the work that we do at ISCA. So I think there's a huge possibility there to build a generalized learning resource of some sort. I don't know what it looks like, but I think it'd be a cool thing to do. Okay, so takeaway, 3 things to remember. Radical co-design is a thing. Like, you really can build 1000x machines. It requires people who are willing to break boundaries, to do vertically integrated research about how to build machines. I don't think we've done it yet on CPUs. I think the reduced precision arithmetic is awesome, and the systolic arrays are awesome, and I think there's plenty more to do in this space. We're just starting to scratch the surface. And the third thing is, maybe this is a big paradigm shift. Maybe this is a Kuhnian revolution, and we'll just take deep learning to be, the metaphors are terrible. People say electricity or fire. I don't think it's that big yet. But maybe it is that kind of change. Maybe, could it be as big as out of order for us? That would be pretty cool. Can we learn enough of deep learning, replace the normal science of our field, And to look back on, tomorrow we get to see the Turing lecture, and Hennessy and Patterson will talk about the quantitative approach. In the first edition of their book, they talked about the El Dorado of the optimized parallel machine, the machine where you wrote your program and it became automatically 1,000 times faster because it just worked through some magic of systems design for hardware and software. We have run out of the widespread general purpose techniques internally. I think out of order might actually have been the last of those for this community, or maybe simultaneous multi-threading, at least for a throughput perspective on things. It's hard to think of the thing that accelerates everything. But what if machine learning actually is of general applicability? What if that list of applications keeps on growing to encompass all of science and all of engineering? Then it is a general purpose technique. And maybe that's a way out of this particular difficult situation. Okay, so I think that's it for the talk. I referred to different research along the way, so rather than put links into things you can see, I have one slide which has a whole bunch of links in it that maybe if you want to take a picture, or it'll be in the PDF as well. Thank you for listening to a roundabout talk. I'd be happy to discuss things and take questions.
Thanks for the interesting talk. I'm really aware of USC. Quick question regarding one of the things that people from embedded systems always have done application-driven design in the embedded system space. So how different is some of the new stuff that you were discussing where you're talking about application drives? It's not just hardware software, but hardware software algorithms and application code design. Do you see strong connections to the embedded systems world, or is it something different, and how is it different?
Right, that's a really good point. I think the embedded systems people have been doing application-specific code design for a long time. A bunch of the fixed point techniques that we used in TPV1 and in the Anton machines are actually well pioneered by the digital signal processing community. And I think it's really interesting that there's actually a divide in the field, that what the signal processing people know and what the scientific computing people know hasn't been fully reconciled, because one works in float and one works in fixed point. I'm surprised there hasn't been a unification of those two sorts of things. But you're absolutely right. And in fact, the embedded space is remarkably cost constrained in ways that forces a discipline, or it makes general purpose cores a luxury in some ways, or makes large amounts of memory a luxury, and the limitations of your bill of materials force you to have, I don't know, to sometimes throw features overboard, and to sometimes say, well, this is just what we can do right now, and the next version will be the one that gets the better thing. Is it different? Maybe not necessarily that different. There's really wonderful stuff in sensing, right? It's not compressive sensing, I'm forgetting the exact term, which is that kind of co-design where you go back to the physics of the photons that are hitting your sensors, and you think about, well, should I do this by putting a lens in front of my sensor, or by doing some other electromagnetic transform on the thing that's going to hit my sensor, or should I do it in post in the digital domain? That's a kind of co-design that is as aggressive as what I think I've been hypothesizing we can do for better TPU design. So, wow, it scared people.
Actually, we're kind of running out of time, so we're actually over time too.
Oh, I'm sorry.
Yeah, but let's thank the speakers again. We're very fortunate to have